Hello everyone. In the previous class we discussed about measurable sets and also we constructed a non-measurable set. Now today we are going to discuss about measurable functions. First of all, let us start with a proposition. Suppose if f is an extended real valued function where domain D is Lebesgue measurable, then the following statements are equivalent. The first one is for any real number alpha, the set of all x when f of x is greater than alpha is measurable. The second one is for each real number alpha, this set where f of x is greater than or equal to alpha for each x is measurable. And the third one is for any real number alpha, the set x such that f of x is less than alpha is measurable. And for each real number alpha, this set, the set of all x where f of x is less than or equal to alpha is measurable. And we have to show these four are equivalent. And these statements imply that for each real number alpha, the set of all x when f of x equal to alpha is also measurable. Now let's prove these are equivalent. First, let us show 1 implies 4. See, suppose the statement 1 is true, that is set of all x when f of x is greater than alpha is measurable. Then this set can be written as, in fact, it is complement of this, complement of x when f of x is greater than alpha, that is d minus of this set, that is your complement. And since d is set of all Lebesgue measurable, I mean d is a set which is Lebesgue measurable, and this set x is also measurable, and we knew that the difference of two measurable sets is again measurable, therefore this set is also measurable. This completes the proof. Similarly, we can show that 4 implies 1. Now let's move on to 2 implies 3. So, set of all x when f of x is greater than or equal to alpha, that is nothing but complement of this set. In fact, this is 3 implies 2. Similarly, you can prove 2 implies 3 also. So this set, which is the difference between two measurable sets, is again measurable. Similarly, you can show 2 implies 3. This is 3 implies 2, and similarly you can show 2 implies 3. Now, we are going to show 1 implies 2. See, the set x when f of x is greater than or equal to alpha can be written as intersection of all those x for which your f of x is greater than alpha minus 1 by n. Suppose if your n is 1, then you will get alpha minus 1. So all those f of x which are greater than alpha minus 1, such an x intersected with when n equal to 2, you will get alpha minus half. All those x values for which your f of x is greater than alpha minus half. If you go on proceed, you will get all those f of x which are greater than or equal to alpha. And in fact, you should note that given the first one, that your x for which f of x is greater than alpha is measurable. Therefore, this set is also measurable. So countable intersection of a Lebesgue measurable set is again measurable. Therefore, this set is measurable. Similarly, you can prove 2 implies 1. Suppose x for which your f of x is greater than alpha, it can be written as union of all those x for which your f of x is greater than or equal to alpha plus 1 by n. When you give n equal to 1, you will get f of x is greater than or equal to alpha plus 1, and when n equal to 2, you will get alpha plus half for such x values. Go on proceed. If you unite them, you will get this, and you should note that this set, because this set is Lebesgue measurable, so the set X for which your f of x is greater than or equal to alpha plus some finite number is also measurable, and the countable union of Lebesgue measurable set is Lebesgue measurable. We have proved these results earlier. We are using it. So we have proved all those four statements are equivalent. Now let's prove the fifth one. Suppose alpha is any real number. Then this set, the set of all x for which your f of x equal to alpha can be written as set of all x for which your f of x is greater than or equal to alpha intersected with set of all those x for which your f of x is less than or equal to alpha. Here it is greater than or equal to alpha, and here it is less than or equal to alpha. Their intersection will be obviously this. And we knew that this set is Lebesgue measurable, and this set is also Lebesgue measurable. So intersection of Lebesgue measurable set is again Lebesgue measurable. This is the case when alpha is a real number. Suppose if because you're choosing your function over extended real valued, your function is extended real valued. So suppose if your alpha is a real number, infinite, then the set of all x for which your f of x equal to infinity can be written as intersection of all those values x for which your f of x is greater than or equal to n. For example, if you give n equal to 1, then you set of all those x for which your f of x is greater than or equal to 1. Then if you give n equal to 2, all those f of x, all those x for which your f of x is greater than or equal to 2. So if you go on proceed, if you intersect them, obviously this will be set of all x for which your f of x will be equal to infinity. Now you note that here in this case your n is nothing but alpha. So set of all x for which your f of x is greater than or equal to alpha, and we know that this is Lebesgue measurable, and the intersection of Lebesgue, countable intersection of Lebesgue measurable set is Lebesgue measurable. Therefore, this is measurable if alpha equal to infinity. Similarly, for the case of minus infinity, you can show that this is Lebesgue measurable. So in general, we say that if alpha is any real number, then this set is Lebesgue measurable. So we say a function which is an extended real value is a Lebesgue measurable function if its domain is measurable and satisfies one of the above conditions, one of the above four conditions. Usually we take for each real number alpha, this set is Lebesgue measurable. We consider this one generally, but you can use any one of them. So when will you say a function is Lebesgue measurable? If the domain of the definition is measurable and one of the four conditions holds. These are the example. The set of all continuous functions with a measurable domain is measurable, and each step function is Lebesgue measurable. You can work it out and put it as an assignment. Now the next theorem is if C is any constant and the functions f and g are measurable real valued functions defined on the same domain D, so your D is measurable, then we have to show that f plus c, c into f plus g, f minus g and fg are all measurable. Now let us prove first one. So we knew that a function is measurable if one of these conditions holds. So you can use any one of them. So we'll use one of them here. So let us define the set of all x for which your f of x plus c, because your function is f plus c, where c is a constant. So f plus c of x will be obviously f of x plus c. F of x plus c is less than alpha. We have to show that this set is measurable. Then f plus c will be a measurable function. But c, you should note that your c is a constant. So let me send this one to this side. So real number minus another constant gives you a constant. So this is of the form set of all x where f of x is less than some real number. And we knew that this is measurable provided your f is measurable. Therefore, this is measurable provided your f is measurable. Therefore, f plus c is measurable. Now let's prove the next one. Here c is any constant this constant may be positive, negative, or equal to 0. So we'll prove for a positive case first. If suppose c is a positive constant, then x, the set of all x where c into f of x is less than alpha can be written as x where f of x is less than, if you send c to this side, alpha by c, a real number by a real number, which is again a real number. So this is of the form x where f of x is less than some real number, and we know that this is Lebesgue measurable. F is Lebesgue measurable, therefore this is measurable, hence this set is also measurable, therefore this function cf is also measurable. Similarly, we can show for the function for the case when c is less than 0. And now suppose c is 0. The set of all x when c of x is greater than alpha, and we know that c is 0. 0 into anything is 0. So your collection of all x which are coming from D with the condition that 0 is greater than alpha. See, if alpha is negative, 0 into anything is 0. So we know that 0 is greater than negative numbers. So for all such x, this is true. Therefore, you'll get all x which are present in D. So this set becomes simply D if alpha is less than 0. For if alpha is greater than or equal to 0, if alpha, for the time being, if alpha equal to 0, 0 cannot be greater than 0. So none of x which are coming from D gives you 0 is greater than 0. Therefore empty. Suppose if alpha is positive, 0 cannot be greater than a positive number. So none of x will come. Therefore, in these two cases, this is empty set. And we know that D is measurable set and empty set is also measurable. Therefore, in any of the case, this set is measurable. Therefore, in all these cases, we have proved that C into F is measurable. Now, let's move on to next one. Suppose if f of x plus g of x is less than some alpha. To show this one, f plus g is measurable. Then send this g of x to this side. F of x is less than alpha minus g of x. You should note that f of x is also a real number and alpha minus g of x is also a real number. Between any two real number, there exists another real number. Let's say it's a rational number r. There is a rational number r such that f of x is less than r less than alpha minus g of x. Now see here, we are having the situation set of all x for which f of x plus g of x is less than alpha, which is nothing but union of, this is we know that this is true provided this is true. So this is nothing but union depending on depending on r, set of all x when f of x is less than r, intersection with, if you send r to this side and minus g of x to this side, you will get g of x is less than alpha minus r. For such x satisfying these conditions, this is true. But we know that this is of the form set of all x when f of x is less than some real number, intersected with set of all x when g of x is less than some real number. We know that f and g are Lebesgue measurable, therefore their intersection is also Lebesgue measurable, therefore their union is also Lebesgue measurable, hence this set is Lebesgue measurable. Now let's prove the next one. F minus g can be written as f plus 1 minus minus 1 into g. Now if you choose this is c, so a constant into g, we know that g is Lebesgue measurable, therefore constant into g is also Lebesgue measurable by second condition, second part. Here we have proved c into f is Lebesgue measurable by that. And just now we proved sum of two Lebesgue measurable function is Lebesgue measurable. Therefore, sum of these two is also Lebesgue measurable. That means your f minus g is also Lebesgue measurable. Now let's prove the last one. What was your last one? F into g is Lebesgue measurable. To prove that, first we show f square is Lebesgue measurable. The set of all x where f square of x is greater than alpha. So by taking square root on both sides, you will get set of all x greater than square root of alpha union with set of all x where f of x is less than minus square root of alpha, because plus or minus will come. So this condition, union of these two will give you this. This is possible, you can write like this, provided your alpha is greater than or equal to 0. If alpha is equal to 0, then your f square of x will be simply equal to 0. So your f of x will be equal to f square of x is greater than 0. So that gives you a simple answer. And when alpha is greater than 0, this is the case. So in any of the case, you will get this. Now the question is, when alpha is less than 0, then set of all x where f square of x is greater than alpha will be equal to domain D itself, as we said here. In this case, if alpha is less than 0, then this set simply becomes D. By the same way, this is D. Now, this is of the form set of all x where f of x is greater than some real number, union with set of all x where f of x is less than some real number. But we know that these two are measurable, therefore their union is also measurable. And this is D, which is a measurable set. So in any of the case, this is measurable. Therefore, f square is measurable. Now we can write fg as half into, if you expand it, you will get fg only. F plus g whole square minus f square minus g square. We have proved f square is measurable. Similarly, g square is also measurable because g is measurable. And sum of two measurable function is measurable. Therefore, the square is also measurable. And we know the difference of two measurable function is also Lebesgue measurable. Therefore, this is measurable. And a constant to a measurable function is also measurable. Therefore, fg is measurable. We have proved all the conditions. Now, let's move on to a next theorem. Suppose fn is a sequence of measurable functions with the same domain of definition. Then we have to show the supremum of all these functions f1, f2, etc. up to fn, infimum of all these, and supremum of fn and infimum of fn are all measurable. Now define a function h as h of x equal to supremum of f1x, f2x, etc. up to fn of x. Then we have to show that this is measurable. Therefore, set of all x where h of x is greater than alpha is nothing but union of each of x which satisfies fi of x greater than alpha. So you will get set of all x when f1 of x is greater than alpha, union with set of all x when f2 of x is greater than alpha, etc. Set of all x when fn of x is greater than alpha. We know that each of these functions are measurable. Therefore, their union is also measurable. That means supremum of f1, f2, etc. up to fn is also measurable. By the same way, you can prove for infimum. Now, similarly, suppose if g of x equal to supremum of fn of x, then set of all x when g of x is greater than alpha is nothing but union of set of all x where fi of x is greater than alpha. That is, if you give I equal to 1, you will get set of all x when f1 of x is greater than alpha, etc. up to set of all x when fn of x is greater than alpha. But we know that each of them are Lebesgue measurable. Therefore, this set is also Lebesgue measurable. Similarly, you can prove for infimum. Thank you.